Let's look at example 2. Here we're going to try to compute the Laplace transform of a linear function, f of t equal to a times t plus b, where the a and the b here are constants. By the definition of the Laplace transform of a function, at plus b in this case, is an integral from 0 to infinity of that function, at plus b, times e to the minus st dt. Again, this is going to be an improper integral, so we have a limit as, let's call it d goes to infinity, integral from 0 to d. I don't want to use a or b here because I've already used them. Limit is d goes to infinity of the integral from 0 to d of at plus b times e to the minus st dt. Now for this one we're going to need to integrate by parts. We can choose u equal to at plus b, which then will mean that du is just a dt. The dv will be the e to the minus st dt. Notice that this is, our variable here is t. So for purposes of this integral, the s is a constant, which means when we find the antiderivative, this is e to a constant times t, we get 1 over that constant, which is negative 1 over s, times e to the constant times t. So our limit will stay here. We do the integration by parts. We're going to get u times v, which will be the at plus b, times negative 1 over s e to the minus st. That'll all be evaluated from 0 to d. And then we'll have minus an integral of v du, but since we got the negative there, we turn it to a plus. We'll have this constant a over s, so we can pull out of the integral. A over s times an integral from 0 to d of e to the minus st dt. Then, still have our limit. When we plug in d here, I'm going to combine all of this together, and I will have a negative, I'll have ad plus b divided by s e to the s times d plugged in for t. Go ahead and put that down into the denominator and get rid of the negative power. Minus, when we plug in 0, we'll have minus a minus, that'll become plus. 0 into here gives me a b times all of this, so it'll be b over s times e to the 0. And then we integrate here. Again, this is the e to a constant times t, so we'll get 1 over that constant. That's going to give me a negative a over, we'll have another 1 over s, so it'll be a over s squared, e to the minus st. Got to evaluate that from 0 to d now. Now let's start looking at this limit here. Notice that both the top and the bottom are going to infinity, and so we're going to use L'Hopital's rule here. Take the derivative of the top and the derivative of the bottom, and we will have derivative of the top is simply a derivative of the bottom will be s times derivative of that, which can be an s squared, e to the sd. This will be plus a b over s minus a over s squared e to the minus sd minus a minus would be plus a over s squared e to the 0. Now this one, as d goes to infinity, that's going to go to 0. We no longer have any d's on the top. Denominator is going to infinity, so this piece is going to go away. That'll stay there. E to the negative sd is going to go to 0. As long as s is greater than 0, so this is going to infinity and that's going to 0. Okay, and so finally we will have that this is equal to b over s plus a over s squared. So the Laplace transform of at plus b is b over s plus a over s squared. And I'm going to just make a note of this at the top of the next page. This is our result that we just had, but there's going to be a couple of important special cases of this that we'll make a lot of use of. The first is that when a is equal to 0, this is just the Laplace transform of a constant, Laplace transform of b. So I'll reduce to this situation. But again, with a equal to 0, this whole term will go away, and the Laplace transform of the constant will just be b over s. So that'll be a useful rule that we'll make a lot of use of. Another special case is if we make b be 0 and a be 1, we're looking at the Laplace transform of t. And again, with b equal to 0, this term will go away. With a equal to 1, we'll just have a 1 over s squared. And so the Laplace transform of t is just given by 1 over s squared. And all of these, just like what we had up here because of that limit, are valid for s greater than 0. That'll actually be the domain of these functions. We're going to make use of these facts a lot in order to help us not have to continue to evaluate those integrals over and over.